All right, let's get into it. Today we're going to talk about something you see all the time but maybe don't really think about, those massive retaining walls. How in the world do they hold back literally tons and tons of soil? Well, it all comes down to a really cool concept called active earth pressure.
I mean, seriously, how do they do it? You see these things everywhere, right? Lining our highways, holding up those fancy terraced gardens. It all hinges on understanding the insane amount of pressure the soil is pushing with. If you mess that calculation up, well, the results can be disastrous. But if you get it right, you can literally hold back a mountain.
And this, right here, is the absolute key to the whole thing. The word you've got to focus on is minimum. See, engineers aren't just trying to build a wall that's strong enough, they're trying to figure out the least amount of pressure it needs to handle. Why? Because that's how you build something that's both safe and efficient. And it all kicks in the moment things start to shift, even just a little bit.
Okay, so let's set the scene here. To really get this, you've got to picture it in your head. We've got our wall, we've got a whole bunch of soil piled up behind it, and then we've got just a tiny bit of movement.
So before anything moves, when that wall is just sitting there perfectly still, the soil is also just kind of chilling. It's pushing on the wall, sure, but it's a neutral, static pressure. It's just hanging out. We call this the at-rest state.
All right, now here's where it gets really cool. What happens when that wall moves? We're not talking a lot, maybe just a tiny fraction of an inch away from the soil. This is where the magic of soil mechanics really kicks in.
It's like a chain reaction. First, you've got the wall moving away, right? That opens up this little bit of space. So what does the soil do? It kind of relaxes. It expands just a little to fill that new gap. And as it does that, something amazing happens. The pressure it's putting on the wall actually goes down. It keeps dropping until it hits rock bottom, its absolute minimum value. And boom, that's your active state.
This quote really nails what's going on inside the soil. As it expands, the little soil particles start to slide past each other. They're overcoming their natural grippiness. That's what we call shear strength. And once that happens, a whole triangular chunk of soil, a wedge, basically breaks loose and starts to slide. That wedge is the thing that's actually doing the pushing on the wall now.
Okay, so we get the concept, but how do you actually put a number on it? How do engineers calculate this minimum pressure? Well, believe it or not, it all boils down to a pretty straightforward formula.
And there it is. Now, I know when you see an equation pop up, it can look a little intense. But trust me, what's behind this is super intuitive. Let's break down what each of these letters actually stands for.
So PA is the pressure we're trying to figure out. It makes sense that it depends on gamma. That's just how heavy the soil is, and Z, which is how deep you are. I mean, the deeper you go, the more stuff is on top of you, so the pressure's higher. Simple enough, right? But the real secret sauce, the thing that makes it all work, is that Ka.
This little guy, Ka, is the coefficient. Its job is basically to convert the vertical pressure from the weight of the soil into the horizontal pressure that's actually pushing on the wall. And what's really cool is that to figure it out, you only need to know one thing about the soil.
And that one thing is called phi, the angle of internal friction. The best way to picture this is, you know when you pour sand on the ground and it makes a little cone? The steepest angle that cone can be before the sides start sliding down, that's phi. It's just a measure of how grippy the soil particles are with each other.
So this stuff is pretty brilliant, right? But it didn't just pop out of thin air. This was figured out over a long time by some seriously smart people. And in this story, there are two names you absolutely have to know. And check this out, this is kind of weird. Way back in 1776, you've got Coulomb coming up with the really detailed, comprehensive theory. Then, like 80 years later, this guy Rankine comes along with a much simpler theory. You almost never see that happen. Usually we start simple and add complexity, not the other way around.
So what this means is that engineers today basically have two main tools in their toolbox for this stuff. So the question is, how do they stack up? Rankine versus Coulomb. Let's get into it.
Really, it boils down to a classic trade-off you see all the time in engineering: simplicity versus realism. Rankine's theory is elegant and simple, but it has to make a bunch of assumptions to work. Coulomb's is a bit messier, but it does a much better job of capturing what's actually happening in the real world. This table lays it out perfectly. Look at Rankine's side. It assumes the wall is perfectly smooth and perfectly vertical, and the ground behind it is perfectly flat. I mean, when does that ever happen in the real world? Almost never. Coulomb, on the other hand, is like, nope, let's account for the friction on the wall, let's deal with walls that are sloped and ground that isn't level.
Because of all those ideal assumptions, Rankine's answer is usually a little higher. We call that more conservative, while Coulomb's is generally closer to the real number.
So, what's the takeaway? It's not about one being better than the other. It's about using the right tool for the right job. If you need a quick ballpark number, or you're dealing with a really simple situation, Rankine's theory is fantastic. But if you're doing the final, for-real design on a complex wall, you're almost certainly going to reach for Coulomb.
And that leaves us with one last question to chew on. Everything we've talked about happens when the wall moves away from the soil, letting it expand and reducing the pressure. But what if you did the opposite? What if you push the wall into the soil, squeezing it? Well, that creates a completely different kind of pressure. Something to think about the next time you drive past one of those giant walls.